analysis tutor. Here we're going to solve the circuit on the board using the node voltage method. And this is something sort of like you might actually see on a test or in a homework assignment. You'd be given a problem like this, fairly complicated as far as we have two voltage sources. We have 128 volts, we have 320 volts. We have lots of resistors connected here, and we already ahead of time have drawn I sub A, IB, IC, ID, IE. So basically, the current in every single leg of this circuit is already drawn for us. And the question might say, find IA, IB, IC, ID, and IE. Find all the currents in the circuit. So if you don't really know what you're supposed to do, you might start trying to fiddle around with Kirchhoff's laws. That's fine. You can use Kirchhoff's laws, but it's going to require a lot of equations. Notice you have a node here, a node here. You have a big node at the bottom. You have all these loops here. So you're going to have to define everything, you're going to have lots of Kirchhoff equations. But what we notice right away is that there's really only three essential nodes. This is an essential node here because it connects three things, so we'll call that essential node 1. This guy is an essential node because it connects three things, so we'll label that with a 2. On the bottom, this is a giant essential node, but again, it's on the bottom. It connects the most number of items, so we're going to call that our reference node. We have to choose one to be our reference. Usually it's going to be at the bottom of the circuit, but it just depends on what the circuit is. In this case, it makes perfect sense for this guy to be the guy. So this is not two nodes down here. Since they're all connected together basically at one point, even though it's not drawn like that, this is one big node, one more node, essential nodes. So we have three essential nodes. So if we wanted to find the node voltages, we're only going to need two node voltage equations. So you might look at it at first and say, well, why are we doing node voltage method? We're trying to find the current. You know, a lot of times in circuit theory, you have to do part A before you can do part B. And you're not really told and necessarily use the node voltage method to find this. Find the node voltages. See, I could easily have written this problem. Find the node voltage at 1 and 2 and then find currents 1 through 2, A, B, C, D, and E. But that's kind of leading you by the hand a little bit. You need to know that if you apply the node voltage method, you're going to be able to find everything else in the circuit. And it's only two equations to find the node voltages, which is going to be much easier than using Kirchhoff's laws. So let's do that now. We're going to find the node voltage here and here. So I want to label it just to make sure we're clear. This is going to clutter up the drawing a little bit, but I'm going to do plus minus V sub 1. That's going to be the voltage, that node voltage there. And then I'll do plus minus V sub 2, and you'll have to realize it's kind of a catty corner guy like this. This is the node voltage there. So we're doing exactly what we've done in the previous problems. It's just a little more cluttered because our original diagram has the currents that we're seeking. We identify the node voltages. There's only two of the node voltages that we care about, one reference guy, and we label them as V1 and V2. That's exactly what we've been doing in every problem up until this point. So let's find the node voltage at node 1. Okay, at node 1, which is this one. Now here's the other thing you got to be careful about. You know, when you're doing the node voltage method, you always have to sum the currents as if they were going away from the node. In this case, it might confuse you at first because you see I sub A is going into the node. So a lot of people will start trying to use that fact and try to figure it all out using the fact that the drawing has the arrows already there. You need to forget what's on the drawing. If there's any currents labeled in any of these drawings, you just ignore them until the end of the problem. Your job when you're doing node voltage is to look at this node and sum the voltages going away from that node. Forget about what is drawn on the paper. We'll get to that later. When you get to this node, you pretend the current's going away in every which direction. And then you find the node voltages, and then you go on and deal with what's written here in terms of the currents. But you have to do the node voltages in a consistent way away from the nodes, otherwise you're going to get the wrong answer. So ignore I sub A. Forget about him. He's not even there. We need to pretend the current's going against this direction and use the same things that we've done before. So that current is going to be V sub 1 minus this voltage, 128. That's going to give me the voltage across the resistor over R. I is equal to V over R. We pop up to our node, subtract any other voltages. That's the voltage across the 5 ohm resistor, and going in this direction, we divide by 5. Plus, the current going through this leg is simply V1 over 60, because that's the voltage across that resistor. the current going through here is simply V1 minus V2 over 4. And this whole thing's equal to 0. We've got everything covered. This current, and this current. This one we pop up and subtract as if the current's going this way. This guy we pretend the current's going this way. This guy we again pretend the current's going this way. V1 minus V2 is going to give us the voltage across the resistor as if the voltage drop were going that way, which is away from that node. Each case we're dividing V over R. So that's equation number 1. Equation number 2, let me actually switch colors just to make it easy to follow. Node number 2, I should say, is over here. So we want to find the current going out this way, and out this way. So going through the 4 ohm resistor is going to be V2 minus V1 over 4. V2 minus V1 over 4. Because we're basically pretending the current's going this way, so we assume V2 is higher. Subtracting off this node voltage is going to give me the drop across the resistor. Divide by 4, V over R, that's going to be it. Plus, the current through this resistor is simply whatever this voltage drop is across the 80 ohm resistor divided by 80, so V over R. But what is this voltage here? Well, this V2, this is another great example of when you need to have a little experience with circuits and sort of the real fundamental understanding of what it means. We've drawn V2 here, but don't forget this is physically connected here, so this voltage here is the same as the voltage here. It's all the same thing, it's joined together. So V2 really is across the 80 ohm resistor. So it's V2 over 80. I is equal to V over R. And that's not something that's given to you or told to you, that's something you have to just know from experience. Now, what is the current through this guy? Well, again, we go up to our reference node, V2 minus this voltage, that's going to give me the voltage across here. V2 minus 320 over R, which is 10. And that's equal to 0. So make sure you understand that. Here, or I should say over here, we go V2 minus the other voltage over 4. The 80 is V over R. And then over here, we go up to our node, subtract this other voltage, that gives me the voltage across this resistor, V over R. And that's it. So these are the two equations, basically, that we need to basically solve. And once we solve them, notice we have V1 and V2. That's all we have. We have two equations, two unknowns, and that is really it. So what we're going to do now is work with equation number 1. Now, let's simplify it. What can we multiply by? What do you think? Let's multiply by 60. Because if we multiply by 60, it's going to wipe this out, and it's going to wipe the other things out too. So we multiply the top equation by 60. We'll multiply 1 by 60, right? Then we're going to get the following. 60 divided by 5 is 12. So we'll have 12 V1 minus 128. Multiply by 60, we'll just have V sub 1. Multiply by 60 divided by 4, you're going to get 15 V1 minus V2. Multiply by 60 over here, obviously you get 0. So we've cleared away all the denominators. Now let's go in here and start distributing and do the simplification. So we have 12 V1 minus 12 times 128 is 1536 plus V1 plus 15 V1 minus 15 V2 is equal to 0. Okay? And now we have a 12 V1, another V1, and another 15 V1. When you sum all of those guys together, what you're going to get is 28 V sub 1. And the only other V2 we have is negative 15 V sub 2. That's it. And then the only constant we have is negative 1536. We'll move it over to the right-hand side of the equal sign, 1536. So this I'm going to circle because this is one of our two equations that we're basically going to use. Okay? So we've basically taken the top equation and made it into something a lot more friendly. Let's go and look at the second equation. What do you think we multiply this guy by to make it simpler? Well, let's multiply by 80. It'll get rid of this, it'll get rid of this, and it'll get rid of this. So what happens when we multiply by 80? 80 divided by 4 is going to give you 20. So 20 V2 minus V1. So let's just write it down. For equation 2, we multiply by 80. All right, so we said 80 divided by 4 is 20, so we'll get 20, and then we'll have V2 minus V1. Multiply by 80 here, we'll just have V2. Multiply by 80 here, we'll just have 8 V2 minus 320, all into parentheses. And on the right-hand side, obviously, it's equal to 0. All right, so now let's do some distribution here. We'll just have 20 V2 minus 20 V1 plus V2, just keeping that along, plus 8 V2 minus, what's 8 times 320? You'll get 2560, and that's equal to 0. Okay, and so finally we're going to write the final equation. We don't have any more V1s other than this one, so we'll have negative 20 V sub 1. What about V sub 2? We have 20, we have 1 more, and we have 8 more. So that's going to be 29 V sub 1. So we've done everything here. We just have the constant. We'll just move it to the right-hand side, 25, 60. And I'll go ahead and sort of circle this guy. Okay? Now, essentially, we're done. We have 2 equations. We have this equation here, and we have this equation here. So let me go ahead and switch boards a little bit and make it absolutely clear. The first equation we have is 28 V sub 1 minus 15 V sub 2 is equal to 1536. We already solved for that. The next equation is negative 20 V1 plus 29 V2 is equal to 2560. Now we want to stick this in a matrix, or if you want, you can just put it in your calculator. If you can get away with that, that's fine. But doing it the matrix way, we want to get down to, we have AX is equal to B. Our A matrix is the coefficient matrix on the left-hand side, so we'll have 28, negative 15, negative 20, positive 29. Okay? Our X matrix, or our unknown matrix, is V1 and V2. That's what we're trying to solve for. And on the right-hand side, we just have what's over here, 15, 36, and 25, 60. So since we know that the solution is going to be the inverse of matrix A times B, then what we're going to basically have is V1 and V2. That's going to equal, what is the inverse of this matrix? When you take this matrix and you stick it in a calculator, hit the inverse button, you will see 0.057, 0.029, 0.039, 0.055. That is the inverse. This is the right-hand side, 1536, 2560. Okay, and now you just finally do the final multiplication of this matrix times this one, V1, V2. When you multiply these guys, what you're going to get is something really nice, 162 and 200. And that's a nice round number, so it always makes you think maybe you've done something right. So when you read it like a book, V1 is equal to 162 volts, V2 is equal to 200 volts. So that's important, but that's really not the answer, because if we go back to our original problem, what were we really asked to do? Find IA, IB, IC, ID, and IE. All right, so that's what we're really trying to find. But what we did is we're always trying to tell you that when you use the node voltage method, once you find the node voltages, everything in the circuit is solved for. That's the only thing required to completely describe the circuit, is these 2 voltages, believe it or not. So we found what those are. Let me write them. This is part of the solution method here. Let me just kind of block it off, and we'll find the remainder of the problem now. What we have solved for, basically, let me put it in red, is that V1 is 162 volts, and V2 is 200 volts. That's what we've solved for. But let's go through now and try to figure out what IA, B, C, D, and E really are. So what is IA going to equal? IA, what's it going to equal? IA is written on the board as going that direction. Now here's where we need to reconcile what's on the paper, what's on your problem from real life, okay? When you see a problem drawn with currents already drawn on the paper, the direction of those currents might be correct, they might not be correct. In other words, it might be totally possible to get a negative value for IA or a negative value for IC or a negative value for any of those currents. And it just would mean that the direction that we drew initially on the paper as part of the problem was actually backwards. That's all it means. It's not means that you're wrong or anything like that. So the way you figure this out is the way it's drawn is telling you that this current really should be going this way. So the way to figure it out would be 128 volts minus this voltage, but we know what this voltage is now. V1 is 162 volts. So this minus this would give me a voltage drop in the direction of this current divided by 5. So it would be 128 minus V sub 1, which is 162. That's the voltage drop across this resistor divided by 5. All right, what is that equal to? So that means that IA is equal to, when you subtract this, clearly you're going to get a negative number. You divide by 5, you get negative 6.8 amps. That's what IA is equal to. We have a negative value. So what it means is that IA really is not flowing this direction. You might say, how is that possible? I mean, you have the power supply here. Why is the current not going this way? Well, in this circuit, you have another big power supply over here that we'll find out in a second is forcing current the other way. So it just so happens that that guy wins and the current really and truly is going this direction in this particular circuit because we get a negative sign there. Let's go and find the rest of the currents and then we'll circle back and talk about it. What would I sub B equal to? I sub B. IB is here. The voltage that we have across that resistor is V1. That's given to us by 162. So V over R is 162 over 60. 162 over 60 is just strictly I is equal to V over R. And so what we'll have is IB. When you take 162 and you divide by 60, you get 2.7 amps. Notice it's positive. That means that the current really is going that direction. All right, so let's go switch back to black for I sub C. I sub C is drawn on the paper as going from this guy across like this. So when we actually calculate I sub C, we have to pretend that this voltage is higher. V1 minus V2 gives me a drop in this direction. So V1 is 162 minus V2 is 200 over the value of that resistance is just 4 ohms. And when you take 162 minus 200, you're going to get a negative number on top. When you divide by 4, I sub C is negative 9.5 amps. Negative 9.5 amps. It's negative because, again, this current actually is going this way. It kind of makes sense when you think about it. This side has a small power supply. This side has a very large voltage. So which one's going to win? Most of the current is going to be going this direction through these top legs, and that's why these things are all end up being negative in the end. So let's find quickly I sub D. I sub D is here. The voltage across this resistor, remember these are connected, so the voltage here is just V2. It's already in the proper direction for a current flow like that. So V2 is equal to 200 divided by the resistance, which is 80. So I sub D, 200 over 80 is 2.5, positive 2.5 amps. Okay, and let's find I sub E. I sub E is right here. So again, it's drawn this direction, so we need to sort of pretend this node voltage is higher. We'll take this node minus this node, divide by here. So this node voltage is V2, that's 200, minus this voltage drop here is 320. That gives me the voltage drop across this 10 ohm resistor, so I divide by 10. And finally, 200 minus 320 gives me a negative number. Divided by 10, I sub E is equal to negative 12 amps. And this is really what we're asked to solve for, all of the currents. So those are the final answers. Notice what's happening here. IA, IC, and IE, they're all negative. So that really means that even though it's drawn this way, IE is going this way, IC is going this way, and IA is going this way. So what's really happening is I have a smaller voltage over here and a bigger voltage here. That's forcing the majority of the current to go this way. This is a positive, so it does go down this way. That's negative, so it's going that way. This guy's positive going that way. That's negative going this way. So the circuit's kind of circulating this direction. The current's going and branching and branching and going around. So it makes total sense physically from what's going on. You just have to be super careful that when you write your node voltage equations, you don't get confused by what's pre-drawn. Because most of the time, let me clue you in, what's pre-drawn on the problem is intentionally there to try to screw you up. I mean, don't you think I knew that whenever I wrote this down, IA really isn't going that way? I mean, I knew that. If you see a problem in your book written with an IA and an IB, chances are it's 50-50 that the direction of that current is not correct. And it's on purpose to force you to get negative answers sometimes for these things. Because if you were given this circuit, you're an engineer working at a company and they say, solve the circuit. Let's say it's so complicated that you don't have this physical idea of what direction things may go. Then all you're going to do is write currents in whatever direction you want. And then you're going to solve the circuit and see if your guesses were correct. In this case, the guesses for the directions of the current, 3 of them were wrong. But that's okay because now I know what the right answers are. And we can redraw the circuit if you want, reflecting the correct directions. But make sure when you write your node voltage equations that you completely ignore any of these drawings that are already given to you. When you write the node voltage here, you have to pretend the current's coming out, V1 minus 128 over 5. This guy over this, V1 minus V2 over 4. Just like we've been doing the whole time. You pretend the current's coming out of this node, pretend the current's coming out from this node. Doing it the same way in both equations gives you a self-consistent system that you can then get the two equations for, use the matrix methods to actually find what V1 and V2 are, and then again, we've said it in the very first section, when you have V1 and V2, when you have your node voltages, you can find anything else in the problem. It's a good example of showing you how. Once you have the node voltages, you can just do subtraction and find the voltage drop across any element, and then you can find the current. Once you know what the node voltages are, then you can say, okay, they're saying IA goes this way, so I'm going to take 128 minus this and figure out if they're right. Turns out they're not right. It was negative. They're saying IB goes this way. Okay, I have a voltage drop there, and so on. And you apply the sign conventions that we've been using to help figure out the subtraction business. I know a lot of that's new to everybody here, and I know that at first when you see, like, what does it mean when they're subtracting? Why is it V1 minus 128? Why is it not backwards? Basically, when you do a subtraction of voltages, you're making an assumption. I'm going to say this again because it's so important. When you subtract voltages, you're making an assumption that, in this case, when I subtract V1 minus 128, I'm assuming that V1 is bigger, right? So that when I subtract this guy, this is going to be a plus and a minus voltage that the current will then flow in the direction I'm assuming it does, right? And so when I make this guy over here, I'm assuming V1 minus V2, I'm making an assumption that V1 is bigger. So when I subtract this guy off, the current is flowing in the direction. I have a voltage drop across 4 ohms in this direction, plus minus. So when you subtract two voltages, you're making an implicit assumption that one side's higher than another, right? So when we write our node voltage equations, we always assume that the current flows out of the nodes. So we're always making these subtractions from going up to our node, popping over, and subtracting. You're going to be doing that the whole time, but you do it for all of your nodes. You do it for all of your equations, and that forms a self-consistent system that can be solved. Sometimes you're going to get negative node voltages. Sometimes you're going to get negative currents in your answers. It just means that the assumptions you made happen to be backwards. Doesn't mean it was wrong. So on your test, you would just circle this. You wouldn't try to redraw the circuit with the correct drawings and all that. They asked you to find IA. Turns out IA doesn't go that way. It actually is negative, so you leave it this way. So make sure you know how this works. Make sure you understand the sign conventions. Make sure you understand the basic ideas of node voltage method. We're going to work a few more of these problems to give you more practice. Make sure you can do them by yourself. So I highly encourage you to, after you watch the lesson, to solve these circuits yourself, go off in your textbook and solve even more. because it's very, very important that you understand the nuts and bolts of how to use the node voltage method. Hello, and welcome to this section of the Circuit Analysis Tutor. Here we're going to continue using the node voltage method that we've been learning to solve this problem, which is on the board. So we have a circuit here, and what we're trying to do is find out what is the total power dissipated in this circuit. And so anytime you're asked a question like what is the total power dissipated, what you need to do is figure out what passive elements, in these case we have resistors here, they're all dissipating some power, so we need to calculate the power dissipated by each one of those resistors, and then we add them all together. So the bottom line is, in order to calculate the power through any resistor, you either need to know the current through the resistor, so the power would be I squared R, or if you know the voltage drop across all of these resistors, you can calculate the power by V squared divided by R. So either way is fine, it's just whatever's more handy to calculate. So what we do is we know that we're going to end up needing to solve the circuit so that we can find either the voltage across the elements or the current through the elements. And so we've been studying this node voltage method. We know that that's going to give us voltages at these key points. And we also know once we find the node voltages, we can pretty much calculate anything else in the circuit. So that's the direction we're going to go. So in order to calculate or to solve this circuit with the node voltage method, we need to identify our essential nodes. So the essential nodes we have are basically here, because we have 4 items interconnected. Here we have 4 items interconnected, and also down here, believe it or not, because we have this resistor, this current source, and this resistor all connected here. So if I were to label my essential nodes, the ones I really care about, this would be an essential node, this would be an essential node, this would be an essential node, because we have 3 or more things interconnected there. So those are the most important points of the circuit. So where do you think, given that, now this is also an essential node here as well, that's definitely true. So I guess I could just put a dot here. So I have 4 essential nodes here. I know from our previous discussion, that I'm going to need 3 node voltage equations, because you need 1 less equation than the number of essential nodes you have. Right? So I have 4 essential nodes, I'm going to need 3 equations. So we have to pick a reference node. Now, you really can do this any way you want. I mean, there's no right answer, right? I'm going to choose to pick this guy as my essential node. I'm sorry, my reference point. That means that all of the node voltages, which really are only these guys remaining, the node voltages that we're going to calculate, they're going to be measured and calculated with respect to this being a common reference point, common ground. You might have probably heard it before. And so that's sort of completely arbitrary, because they're all almost equal. I could pick whatever I want. I could pick this as a reference, and then all the voltages over here would be with respect to this. If I really wanted to, I could pick this as the reference point, and then these 3 remaining nodes would be with respect to this. But typically when you're doing these problems, you want your reference to be on the bottom of the circuit, and then your node voltages to be somewhere up around the top of the circuit. It helps you visualize how to write the equations, but it's certainly not strictly required. So this is going to be our reference, and we have these 3 remaining nodes. So I'm going to label this node number 1, and I'm going to label this plus minus V sub 1. So that's node 1. V sub 1 is what we care about here. I'm going to call this guy node 2 plus minus V sub 2, and you kind of have to use your imagination that it's catty corner, measured with respect to our common reference point here. And then I'm going to call this guy node number 3 plus minus V sub 3. So it clutters up the drawing a little bit, and I try to use different colors to show you. What you're given in the problem is that everything in black. Everything in red, you have to do this yourself. And like I said, you could pick this as your reference node if you really want to and do everything. It's just then you'll be kind of writing your equations kind of upside down, so to speak, when you're going through the node voltage method that we're talking about here. So let's go ahead and write the node voltage equations, try to solve the circuit, and calculate the total power dissipated. So, and before we get started, I noticed one small change I want to make. I'm going to put plus and minus on the top, and that's going to make this problem a little bit more interesting. That's the way it should be drawn. So in fact, before we get started, I'm switching the polarity, so it's almost like you take the battery, if it's plus minus, and you flip it around the other direction. That's why we have minus plus right there. So what we want to do is write the node voltage equations. We have 3 of them, and we're going to write them right now. So at node 1, what would the node voltage equation be? Well, we want to calculate and figure out what is the current leaving node 1 in all directions. So first we look at this direction. We pop up to voltage V1. We subtract off the voltage on the other side. That's going to give us the voltage drop across this element. Now this is a little tricky, specifically because I've flipped the polarity around here. If this were plus minus, which is what every other problem we've done before has been, or most of the problems, then all you would do is you would take V1 minus 40 divided by 12. And that makes sense because if you have a 12 ohm resistor and you have a voltage on one side and a voltage on the other side, if you subtract the voltages, then what you're getting is the voltage drop across that resistor. That is perfectly fine to do whenever this is, plus minus, because you're popping up here, you're subtracting off some other voltage, that gives you the drop, okay? The only difference here is that we've reversed this. So you're still subtracting, but you have to subtract a negative 40. So it's a minus because we're subtracting the voltages, but it's minus 40 because I've flipped it around. So you need to get in the habit of, when you're doing node voltage, most of the time you're going to be going voltage minus some other voltage. When it's plus minus, that's going to give you the drop across the element you want. If it's ever reversed, then you'll have to, basically what you're doing is adding them together. And I'm showing you explicitly minus a minus so that you're not confused, but really what you're doing is you're just adding them together. All right, so pop up to V1, subtract this voltage happens to be negative, so there you go. And then you divide by 12. So what we found is the current flowing through this leg here. Next, what is the current through the 25 ohm resistor? So it's plus V sub 1 is that voltage over 25. Okay, great. Next we have the current going through here, which is leaving the node, so it's just a plus 5. We always write the node voltage equations with respect to the current leaving. And now we have the 20 ohm resistor up here. So you pop up to V1, subtract V2, that's going to get you back down to your reference point and give you the voltage drop across there, and you divide by 20. And that's equal to 0. So that's the node voltage equation for node number 1. All right. Now, node number 2 is this guy over here. We want to find the current through this leg, this leg, this leg, and this leg as if they're flowing away. So first, let's go this direction. So in order to find the current through this, we're going to pop up to V2, subtract V1, V2 minus V1 over 20. Okay, so that's the current going through there. Next, what would be the current from this leg here? Well, typically we're looking for the current leaving the node. This current's going into the node, so it's going to be minus 5. So everything's consistent. This was plus 5 because over here we had the current leaving this node. Here it's entering this node, so we go minus 5. Next, we want the current to flow through this 40 ohm resistor. So we pop up to V2 minus V3 over 40. Right, so then we're subtracting these voltages divided by this guy, that's V over R. It's going to give us that current. And then finally we have 7.5 amps going into this node, so it's negative 7.5 equals 0. So that is the node voltage equation for node number 2. And then finally for node number 3 is this node down here. This is a little bit simpler because we only have 3 legs, so we're going to have less terms. So first let's figure out what is the current through this 40 ohm resistor. So we go V3 minus this voltage V2, that gives us the drop over here. So it's V3 minus V2 over 40. So remember, you always pop up to your node, subtract another node from it, and then you have divided by R, so V over R. Next, we have 7.5 amps going out of this node, so it's going to be 7.5 amps going out of the node. And then finally, we have the current through here, which is just simply V over R, V3 over 40. So this, again, has one less term because of the fact that it's a simpler node. So these are the 3 node voltage equations. And again, if you want to solve it, you basically can solve these equations any way you want. What we're trying to do is find V1, V2, and V3. Once we have them, we're going to immediately know some of the power dissipated. We'll know the power through the 25 ohm resistor, V squared over R, right away. We'll know the power through the 40 ohm resistor, V squared over R, right away. Some of these other resistors we'll have to subtract voltages to get the voltage across it, but we'll do V squared over R. For all of the resistors, we'll get the total power dissipated. So you can do it any way you want. I usually do it with matrix methods. If you have a solver in your calculator, you can use that. These equations are all fractional, and they're a little bit ugly just because of the way the node voltage method is set up. So what we want to do is correct this problem. So what we're going to do is go off to the next board and work with each equation specifically. So what we're going to do now is go work with equation 1. And what we're going to do for equation 1 is we're going to multiply by 25. So we look over here and we look at the denominators, and sometimes we can do pretty good, sometimes we can't. This is a case where we really can't. You can't pick a perfect number without a lot of effort. So just multiply by 25. That's going to eliminate this for sure. This will be a nice number. This will be not so nice. This will be not so nice once we multiply by 25. We do the best we can. We try to avoid having decimals running around our equations, but it doesn't always work. So multiply by 25 over here, we're going to have 25 divided by 12. That's going to give you, let me switch colors over here. That's going to give us 2.08. And then in parentheses, we have V1 minus a negative 40, which is V1 plus 40. All right, and we multiply by 25 over here. It's just going to clear this out, giving us V1. Multiply by 25 here, we're going to get 125. Multiply by 25 here, we'll have 25 over 20, giving us 1.25. And in parentheses, we still have the V1 minus V2, and that's all equal to 0. So that is the first doctored equation. So let's multiply inside here. We'll have 2.08 V1 plus 2.08 times 40 is 83.2. Then we'll have plus the V1 here, plus the 125, plus 1.25 times V1, 1.25 V1, 1.25 times V2 equals 0. So we have the entire equation there. And basically we have some terms in V1 here. When you add the terms in V1, the 2.08, here's one more, here's 1.25 more, you'll get 4.33 V1, all right? The only other V2 we have in here at all is this one, so we have minus 1.25 V2. And then over here, we have 83.2 plus 125. You add them together, you're going to get a positive number. You move it to the other side, you'll have negative 208.2. So that is sort of the simplified form. I'm going to put a little star by it because that's what we're going to use here in a few minutes to actually solve. So basically all we did is we took equation 1, we multiplied through to kind of get rid of everything, and then we simplified the terms, and this is sort of node voltage equation 1 after we've done the simplification. So next, let's go and do node voltage equation 2. So over here we look, now this is a lot nicer. If we multiply by 40, we'll eliminate this. This will be a number. 40 divided by 20 is a nice number, so we're going to have a nicer set of equation here. So let's multiply by 40. When we multiply by 40 here, 40 divided by 20 is 2. So what we'll have, let me write down, multiply by 40. And let's change colors just to make it absolutely clear what we're doing. So what we'll have is we'll have a 2 over here. So when we multiply by 40 over here, we will have 40 divided by 20 is 2. So what we'll have is 2, and in parentheses, we'll have the V2 minus V1. Multiply by 40 times 5, we're going to get 200. Go ahead. Negative 200. Over here, we'll multiply by 40, and that's just going to eliminate it. So what we'll have is V2 minus V3. And then we multiply by 40 here. 40 times 7.5 is 300, so negative 300. And we're going to set this all equal to 0. All right, so this is a little bit simpler immediately, you see, because we have these nice whole numbers. So we have 2V2 minus 2V1 minus 200 plus V2 minus V3 minus 300 is equal to 0. So hello and welcome to this section of the Circuit Analysis Tutor. Here we're going to solve this problem on the board, what we have labeled already with a few different currents. So we have a 20 volt source, we have an 11 milliamp current source, we have a 10 volt source which is actually kind of backwards, so we have minus and plus. This problem also has larger resistors, so this is 1 kilo ohm, 1,000 ohms, here's 25,000 ohms, and some larger resistors here. Now we have already pre-labeled I1, I2, and I3, and this problem very simply states, let's calculate I1, I2, and I3. How do we find the currents there? You'll quickly figure out, trying to do this thing by other methods, that it's going to be very difficult to use, just regular Kirchhoff's laws or whatever. I mean, you can solve any circuit using those methods, but you have lots of equations, lots of unknowns. So we're going to, again, turn our attention to the node voltage method. I'm also going to say up front here, though, that this problem is kind of like what you get into on a test. You can solve a few simple node voltage problems in your homework. You're like, piece of cake, I've got it. You write your equations, you write your unknowns. Bam, you solve these equations, you get your node voltages, you're done, you're ready for the test. But what you're going to find is that your instructors are going to start throwing stuff like this at you. It looks simple at first, but as I walk through it with you, it'll make you scratch your head once. And when you see the aha moment, you'll be like, oh, that's so easy. Well, that's how it always is in math and science. I mean, things seem difficult, scratch your head, and then you say, oh, aha, I get it, after somebody explains it to you. So my advice to you here is, if you don't see, when we get to the point in the circuit where you realize it's a little difficult, if you don't see it, that's okay. We learn by doing. And if you do see it, like if you look at this and say, oh, I get immediately what to do, then congrats, you're ahead of the game. So let's take it one step at a time and solve this just like we're going to solve any node voltage problem, because that's what you're going to do in a test. You're going to go by that memorization of what to do. Let's do it just like we've been taught, and then we'll see if any roadblocks come up along the way, and I'll just give you a hint. There will be one at least. So where are our essential nodes? Okay, so well, here's definitely one. So I'll call this node 1. Whoops, let me erase this guy right here and just put a big 1 with a circle. So I'll call that guy node 1. What other essential nodes do we have? Well, this, if you look at the bottom of the circuit, you might say, well, this is an essential node, and it is. So this is sort of an essential node down at the bottom, but realistically speaking, I'll just tell you right now, we're going to use this as our reference. So we're not really going to, and that makes most sense because there's no resistors down here. We like our reference to be on the bottom if we can. And it interconnects with a lot of different things. So it makes sense to have it at the bottom. So what other essential node do we have? Well, you might say, and this is sort of the first quote-unquote roadblock, you'd say, well, I have an essential node here and an essential node here. Bam. If you make that mistake on a test, it's going to cost you, because you really have to look at what you have here to make sure. What you have here for this node is you have a current source and a resistor, but the thing connected over here is just a wire. Right? So it doesn't really count as an essential node by itself. At least it's not too compelling as an essential node, because usually for these essential nodes we have 3 or more actual devices, resistors, current sources, whatever, connected together. Here we don't quite have that, so it doesn't quite fit that cookie cutter mold. We have current source, resistor, and sort of nothing here. And then we look over here and we say, well, this is certainly an essential node, right? But when you look carefully, you have a resistor connected to a voltage source, connected to, again, nothing. So this is sort of kind of an essential node, and this is sort of kind of an essential node, but they don't really follow our definitions of what we've seen in past problems. So that's what's going to happen on your test. You'll get a problem, and you'll be like, well, this is a little different. I've never quite seen this before. It's kind of like algebra. You get to equations that you haven't ever seen before. So as we work these things, you'll put them in your back pocket. You'll see how we handle these situations, and you'll be really well prepared for your exam. The secret to this, I mean, there's probably more than one way to do it, I'll be honest with you. But the way I do it is I treat this entire thing as a single node. And that's kind of hard to believe at first, but when you think about it, this thing is connected. Let me put my paper down here. This thing is a perfect wire, no resistance here, right? So it's the same thing as if I were to take this intersection and take this intersection, and if I could physically join them together at one point right in the middle, that is how it's actually connected if you were to build this circuit. This is physically connected here. It doesn't matter that it's drawn far apart. That's just for display purposes. That's just because when we draw circuits, we like them to be nice and orderly. If we were to draw them at one point, then I would have to slant everything in, draw this resistor crooked, draw this guy crooked like this, and then join at a point here, and it just wouldn't look very pretty. If I drew it like that, though, if I drew it where everything came to a point like that, it would be very easy for you to understand how to proceed, because you would immediately identify this point as an essential node, because it would connect all this stuff here plus all this stuff here at one point, and you'd say, oh, well, yeah, of course that's an essential node. You go and solve the problem like that, right? But it's not drawn like that. So what I'm going to do is, this is sort of maybe different than some books might show you, but I'm going to put the node here. I'm going to call this my second essential node. And I'm doing it here in the middle, mostly to remind myself, as I look back, that I have to deal with this stuff over here, and I also have to deal with this stuff over here. So that's why I'm kind of putting it in the middle. There are no other essential nodes in this problem. Your first thought is, here's a node, but they don't quite connect enough things to be what we call essential nodes. So we're going to say, oh, they're connected together. It's one giant node. Down here, it's the same thing, down here and down here. This looks all spread apart, but in reality, it's all connected together at one common point. So the fact that I put my reference here, the reference can be here, or it can be here, it can be here, it can be here, it can be, it's all connected. So it can be anywhere down here. I'm just drawing it here. So it's kind of an aside, but it's super important. So I have two essential nodes up here, plus the one that I'm counting for my reference, so I know I'm going to need two node voltage equations. All right, so let's go and proceed just like we would typically. All right, so over here at essential node 1, what would be the node voltage equation? So we're looking at the current going out, 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 and out. For now, you completely ignore what is drawn in the picture. The picture is what I'm trying to supply as an answer, right? But the node voltage method requires that you write your equations as if the current is leaving the node. So write them that way. Get the answers, and then later on when you're trying to tell the teacher what these currents are, then you'll reconcile it with what's on the paper. Because half of these currents might be drawn backwards on purpose just to confuse you. And they probably are. So let's find the current here. We have to label, first of all, before we do that, let's label this as node voltage V sub 1, and this guy I'll just put plus minus V sub 2. Notice this is all connected together, so I'm putting a plus sign here, but the node is really all this stuff over here, and you'll see how we handle it in a second. All right, so here, we're going to pop up to V1 minus 20 volts over 25 kilo ohms. So you don't want to put 25, you want to put 25 times 10 to the 3. You always want to work in ohms. So subtracting this minus this gives you the voltage over there, V over R. It's so far the same as we've done before. Plus, what is the current going through here? It's V over R. So we have V1 over, what is the resistance? 250 ohms. So V1 over 250. Next, the current going through this leg is going out, so that's good. It's 11 milliamps. You don't want to use 11. You want to use 11 times 10 to the minus 3 because that's milliamps. So it's a little bit ugly having the scientific notation, but there's really no way to avoid it. I mean, if you have kilo ohms, you got to deal with thousands of ohms. I mean, it's just a very large resistor. If you have milliamps, that's, 1/1000th of an amp. Okay, the final guy is this one up here, so we'll put a plus sign. How do we find the current going through here? Well, we have to find the voltage across this resistor. So we look here and we say, how do we find the voltage across this resistor? Well, we know we have V1, so let's write this. And if we go all the way to the other side, we see that we know the voltage all the way from this point all the way down to the common ground. So if we take this minus this voltage, that gets us what we want. So we'll have a minus, and since this is written in the negative sense with negative positive, it's going to be negative 10. And then it's going to be divided by the 500 ohms equals 0. So again, take this voltage here, pop up here, and then we subtract the voltage on the other side, which is known as negative 10 volts. Now, just to keep the board clean, this is V1 minus a negative 10, right? I'm going to go ahead and put plus here, so really it's going to be V plus 10, but I don't want to write this again one more time just to tell you that. So I'm just going to put it like that. So this is the node voltage equation for node number 1. So now what we need to do is write the node voltage equation for node number 2 over here, and then solve the system of equations and go from there. So let's just proceed as we normally would. The only difference really is that you need to consider this entire thing a common node. So that means I'm trying to find the current leaving the node. That's what node voltage is. Always have to find the current leaving the node. So if you consider this entire thing a super node, so to speak, you know, a giant node, then this 11 milliamps is going into the node. So it's going to be a negative 11 milliamps, 11 times 10 to the minus 3. Yes, it's way over here, but it's going into the common connection point that we're calling this big supernode over here. All right. Next, we want to find out what is the current through this leg. So we have V2, that's the voltage across this. V2 over 1,000. I'll just write it as 1,000. That's V over R that gives me the current through there. All right. So I've got this leg and this leg, everything we're cooking with gas so far. Next, I want to find out what is the voltage. Let's say, or I'm sorry, what is the current through this 500 ohm resistor? Because notice, this is one giant node. So we found the current here in this leg, the current here coming out of this leg. Now, remember all this stuff is connected to this big node here, so we need to figure out what is the current going out through here and also out through here. So the current out through here is going to be V2 minus V1, V2 minus V1 over 500. So again, we pop up to our node voltage V2, and then we subtract V1. That's going to give us the voltage across the 500 ohm resistor. So everything's the same so far. We have current going in. We calculate this with this term. We calculate the current going out of this guy over here. It's just that this node is kind of stretched out. That's all we're doing. Finally, we need to find out what is the current through here. So we start looking at this, and we quickly get a little bit stumped. Because typically with node voltage, either you have a current source, right, telling you what the current is flowing in or out of the node, or you have a way to subtract voltages and divide by a resistance, you know, like this minus this divided by 10 ohms, that's the current in a leg. You can't do that here because I'm trying to literally, I need to know what the current is here, right, but it's completely unknown. I can't pop up to V2 and subtract anything. I mean, there's nothing to subtract, you know, it's just there, right? So how do I find the current flowing in here? It's very difficult for me to figure out how to do that. So what you end up getting is stuck. And this is what I was saying. I want to solve this problem exactly how I would on a test, right? And show you how you're basically going to get stuck. I don't really know exactly how to do that. How do I find this? Now I know ultimately it's going to be I3. If I put I3 here, that doesn't help me because I need two equations and two unknowns, V1 and V2. If I put I3 here, it's just going to introduce a third variable, I3. How am I going to solve that? It's going to be difficult. I mean, there are ways to do it, okay? You could look and write more equations for I3 and try to get even more equations, but it's difficult to look at. So at this point, anytime you get to a point in a problem where you write everything down and you're totally out of your league as far as never seeing anything like this before, you need to really look at it for a second. And it took me a few minutes actually to realize that this problem is actually much simpler than it seems. Because if you look at this, the way it's drawn, V2 is the voltage up to this essential node up here, right? But this voltage source here is across the same points. Because this is all connected together here, this voltage is V2. It is exactly equal to V2 because everything's connected in parallel. Remember, we talked about this a long time ago. When you have things connected in parallel, by definition, the voltage across them has to be the same. So if there were a resistor here, then this problem would be totally different, and then that would not apply because there's something in the way. But since these are in parallel with one another, then V2 is actually equal to negative 10 volts. And that's so important, I want to actually write that down. V2 is actually equal to negative 10 volts. And this is so important. So in fact, you know, I said, hey, there's two node voltages in this problem, V1 and V2. You found one of them without solving any equations, right? So if you happen to see this ahead of time, you know, when we first wrote the problem on the board or in your test, you just see it and you're like, oh, that makes sense. Write it down. Go for it. Write it down and go for it because I just wanted to show you the thought process of what would happen if you just kind of ignored that and didn't see it. And you're going to get stuck. You're not going to be able to do anything here. So you see V2 is equal to negative 10. Now, that's kind of neat. That helps us. Then we say, well, how am I going to find V1, right? So you start looking at this and you start looking back and you realize, look at this equation. This equation has V1, V1, V1. There's no V2 anywhere in this equation at all. That by itself makes it different than any other node voltage problem we've done before. Usually we write node voltage problems, we have two variables, two unknowns, and each equation has both variables. So you have to use matrix methods or something to solve the system. This one's different. It doesn't actually involve anything except for V1, and it's that way basically because of this over here and the way everything's constructed to set this up for you. So actually, you could just solve this equation by the rules of algebra and calculate V1, and then you would have V1 and you already know V2. Bam, the rest of the problem can be solved. Once you know the node voltages, you know everything. So that is what we want to do. Let's take this guy, let's go with purple. We're going to take this equation and we're going to solve it. How we're going to solve it? Well, we've got lots of fractions everywhere. We want to clear these denominators out, and it's not going to be pretty, but let's multiply by 25 times 10 to the positive 3, 25 times 10 to the 3, because that's going to clear the most stuff. Multiply by 25 times 10 to the 3. All right, and when we do that, let me grab another color here. We multiply by 25 times 10 to the 3 here, we're going to get V1 minus 20. Multiply by 25 times 10 to the 3 here, it's going to be that divided by 250, which is going to give you 100 V sub 1. That's a nice number. You multiply this by 25 times 10 to the 3, you get a nice number of 275. Multiply by this by 25 times 10 to the 3, divide by 500, you're going to get a nice number of 50. V1. And notice it's minus a plus, so it's just going to be plus 10 equals 0. So this equation looks a lot nicer. So even though it will take a little time, let me just rewrite it again. Minus 20 plus 100 V sub 1 plus 275 plus 50 V1 plus 500, because we multiply these guys together. Okay, now we add everything together. If we take this V1 plus 100 more plus 50 more, we'll get 151 V sub 1. Negative 20 plus 275 plus 500 is going to give you 755. Let's move it to the other side of the equal sign, and you're going to get negative 755. Because you'll have a positive number over here, you move it over there, you get negative. And so at the end of the day, V sub 1, when you divide this out, you will get negative 5 volts. So basically, whenever you take negative 755 divided by 151, and in that case, you get negative 5 volts. And you know at this point that you've done something right, because this problem, which looks very complicated, suddenly you get a nice number for V1 and a very nice number for V2 as well. So you've solved the node voltage problem. But notice how easy it was. You didn't have to do matrices, you didn't have to do anything, and it's just because of the way this problem is constructed. Physically, the way everything's constructed, to be able to find the currents here, it only involved V1. When you tried to write a node voltage equation here, you couldn't, right? Because you couldn't figure out what the current was in this leg, but then you realized this voltage is equal to the node voltage. And then when that revelation kind of leads to what's going on. So you've solved the node voltage, you know V1 and V2. Right? How do we go about finding these currents? Well, that's just going to amount to a little bit of subtraction and figuring out, what the voltage is across the resistor elements divided by R is going to give us the currents. So as an example, let's look at I sub 1. How do we find I sub 1? Well, it's drawn as if it's going this way. Now, this is an important distinction. When we do the node voltage method, we always assume the current's going out of the node, right? But we only do that to write our equations consistently and find the answers. Now we know V1, as drawn in this drawing, we know it's negative, but we're not going to erase everything and flip it around. That'd be just dumb. We want to leave it the way it is, but we just know the answer is negative. So now, to make it easier on yourself, you know that you want a current written as if it goes this direction. So let's just take 20 minus V1. That's going to assume the current's going this way. Remember what I said before. Anytime you subtract voltages, you make an assumption. When I subtract 20 and I subtract this one from it, I'm making an assumption that this is the bigger voltage, so the current's going that way. So let's take 20 minus V1, and that's going to give us a voltage across the 25K resistor. So what we're really going to have here for I sub 1, what we're going to have, I sub 1 is going to be equal to 20 minus V sub 1 over the resistance, 25 times 10 to the 3. I'm taking 20, I'm subtracting this voltage from it, that's going to give me the current flowing this direction divided by R, V over R. Now, the only catch here is minus V1 is a negative number, so you get negative 5 over 25 times 10 to the 3. But this is okay because this is basically just 25, right? So if you take minus negative 5 is going to be a plus, so 25 divided by this, then what you're going to get 0.0010 amps. All right, and well, let's just do it like this. So I sub 1, if you look at this, if you shift the decimal 1, 2, 3 decimal places, what you're going to get is 1 milliamp. And that is I sub 1. That is the answer. 1 milliamp, or 0.001 amps, however you want to say it. Now, this whole subtraction business, it gets people, it gets people confused. A lot of times whenever you solve the problem, you have a negative node voltage, your current is drawn in the circuit opposite of the way that you solve the node voltage problem, it can get confusing. You need to separate the two, right? When you solve your node voltage problems, you pretend the current is leaving the node and you get an answer. Then, separately, whenever you try to calculate a current like as given and drawn in a problem, you need to assume the current's going this direction, right? So, to do that, you subtract this minus this. It just so happens that this is a negative number. Let the algebra do the work for you. In other words, some students try to overthink it, and they think, well, this was negative, the current was that way, so I need to subtract it this way so that I can get the right. No, 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 no. You look at this voltage, you subtract this voltage, that gives you the current in this direction. Okay, V1 happens to be negative. Let the math take care of the answer, right? Turns out our current is a positive number. So that means our current really is flowing this direction. And there you go. So let's go and find it for I sub 2. For I sub 2. All right, I sub 2 is pretty easy because V over R is very simple. V is V1. So I sub 2, I'm sorry, yeah, V1. V1 over R, which is 250. Again, let the algebra do the work for you. What is V1? V1 is negative 5. Negative 5 over 250. All right, so what do we get when we do negative 5 over 250? We'll get negative 0.020 amps. You can circle that if you like, that's fine. But if you shift the decimal 1, 2, 3 decimal places, you'll get negative 20 milliamps, and that is the answer. Now notice this is a negative number, so that means that this I2 as drawn is actually backwards. It means the current's actually going up this direction, okay? Kind of makes sense. It's going up, it's joining with, well, this is actually, yeah, this is going this direction because we got a positive number. We got a negative number, so this one's going up. So these guys are joining together. Some of it's going this way, and so on. And so you let the algebra and the math do the work for you instead of trying to think which direction's the current going. You just do the subtraction, deal with the signs as they pop up. Now, we need to know what I sub 3 is over here. Now, this is the toughest one of all because we don't have a V and an R to just do I is equal to V over R, right? We can't do that. So we can't just do it, okay, this voltage, this current, this resistance, and we'll just get it by Ohm's law. We can't really do that. So we end up having to use a little bit of thought. We know Kirchhoff's laws are always true. Kirchhoff's laws are always true. That means at a node, the current going into the node has got to equal the current leaving the node. It's like water in a hose. Water goes in, water goes out. Even if you split it with a Y splitter, water goes in, water goes out. The sum of them have to basically, the algebraic sum has to be 0, which is the same way of saying the current coming in has to equal the current that leaves, even if it branches out, right? This is conservation of mass, really, because the charges are coming in and leaving, right, or conservation of charge. So we need to think of it this way. Okay, we're trying to find this guy. We know what this current is. We don't know what this current is here, but we can calculate it because we know the voltage here, so we can figure out the current here. We can also figure out the current up here, and we know that this current is going to combine with this current, is going to combine with this current, because everything is going to go through this wire. Everything coming up through here is going to go through this wire and join with the 500 ohm current. All this stuff is going to come through and make this I3 current. So really, what we need to do is, even though it's not stated, in order to calculate this, when you're going to need to calculate this current and this current to be able to sum them together to give us this. That's the bottom line. All right, so that's what we're going to do now. And there's many ways to do it. I try not to skip steps. I try to make it clear for myself, so I'm going to do that here. And this may be a little too slow for you, but this is how I'm going to do it. I know I'm going to need the current through the 1 ohm resistor, so through the 1K resistor. So the I through the 1K resistor is going to be equal to V2 over 1,000. V2 is given in our problem by negative 10. right? So what I'm going to have is negative 0.010 amps. I don't want to convert it to milliamps yet because I'm still going to add it to a bunch of other stuff. All right, the other thing I'm going to need is the 500 ohm resistor current, because that's going to join up here and go down. So I want to calculate that by taking V1 and then subtracting this known voltage over here. That's going to give me the voltage across here. So the 500 ohm current is going to equal V1 minus this voltage. You've got to pop yourself all the way over the resistor to this voltage, but it's flipped backwards. So it's minus a negative 10 over 500. And of course, anytime you have subtracting a negative, it's the same thing as addition. So what you have is V1 is given to us now by negative 5. So it's negative 5 plus 10 over 500. So what we have is 5 over 500. And when you take 5 over 500, you will get 0.010. 0.010 amps. And this one's positive. So don't worry about the fact that this is negative and this is positive now. It's okay. We're basically pretending. Let me draw a few things on this drawing here. When we did this, when I just calculated the 1K, I was basically pretending that the current flows this direction. So I'm going to call this I1K. The reason I pretended that is because I did V2 divided by this resistance. Forget about the sign of V2. Just by the drawing, if you have a voltage drop here with plus on the top, minus on the bottom, it means the current's going down. So I'm going to draw this way. Over here, I subtracted V1 minus something over here, so that means I basically assumed implicitly that this is the 500 guy here. Okay, so I have enough to do the final calculation now. So what I'm going to do is label one more thing. These guys are going to basically sum together to give me the current flowing through this wire. I'm going to call it I wire, right? Because it's going to join up over here. I could do this all in one step, but I wire, what's it going to be equal to? It's going to be equal to the 11 milliamps, 11 times 10 to the minus 3. And I subtract the current from here, because if I take the 11 milliamp current and I subtract the current that's flowing away, what's left over is going to be what flows in I wire. So I'm subtracting the 1K, current. So I'm subtracting a negative 0.010. So I wire, because subtract a negative gives you a plus, you're going to have 0.021 amps. Okay, that's the current flowing through that wire. And when I say flowing through it, I mean flowing through it in this direction. So now it's very simple to see what happens, because I have the current going through this 500 ohm resistor into this node, combining with the current that's flowing through this wire. These two things summed together must be the current flowing through I3. So the way you write that is I3 is equal to I500 plus I wire. I500 is positive 0.010. I wire is 0.021. So I3, when you add these guys together, 0.0310 amps, which is equal to, if you shift the decimal 1, 2, 3, 31 milliamps. And let me circle that, because that is our final current. This is our final answer. It's a little bit confusing at the end how to approach it, but my advice to you is, like I said again and again, trust the algebraic signs, trust the math. Don't overthink and try to flip currents in your head and so on. So what you're really trying to do is you're trying to find the current. I3 is drawn as it's going down, all right? So I had to somehow figure that out. I needed to add these currents up, but it gets confusing, so what you need to do is do some labeling. Remember back to physics, when you had all the pendulum problems and the ramp problems and everything else, you had to draw your vectors and you had to kind of invent your own variables. Oh, I'm going to call this theta, and then I'm going to use it, and then I'm going to find what I'm trying to find. You had to kind of use your own intuition and knowledge and make your own variables up, basically, to solve it. So that's what I had to do here. You're not asked what this current is, and you're not asked what this current is, but it quickly becomes apparent that you need it in order to find this. So let me go ahead and draw it this way. I have to draw it this way because V2 is on the positive side. So if I do V2 divided by R, that's going to assume the current's going down. So when I do that for the 1K resistor, it happens to turn out negative, only because V2 was negative. So again, just to be clear, this current, because it's negative, really is going up, but that gets too confusing to sit there and flip, oh, it's really going up. No, no, no. Use the drawing and just keep your signs there, right? The 500 the current there is just V1 subtracting off this voltage, which is also negative. So you subtract this negative voltage divided by the 500 ohms. And so when you do this math, you get a positive number. So you get a positive number for this current, you actually get a negative value for this current, but that's okay, because what I'm going to do is I'm going to say 11 milliamps minus this current is going to give me this intermediate current that I'm calling I wire. This minus this negative number, which ends up being a plus, because remember, this is really flowing into the node. That's why you're really adding them together. You just let the algebra take care of it. You get this positive number. So this current flowing in this I wire is 21 milliamps, basically. And it combines with this current up here. So what you have is 21 milliamps plus another 10 milliamps gives you 31 milliamps in the end coming down there. So it's an interesting problem on multiple levels. It's one of those things you look at. It doesn't look any more complicated than any of the other node voltage problems that we've done. And that's the fallacy of electric circuits. You look and you cover the surface, you skim the surface of the solution method, and you're like, oh, I've got this, it's just algebra, right? But then you start doing things like this and you need to know, how do you handle the signs? How do you handle the current directions? How do you know how many equations to need? How do you handle it when a node is kind of separated by a wire like this? Do I treat it as one big node, or do I treat it as two smaller nodes? What do I do? Nobody's born with this knowledge. So look at this problem, get some intuition from it, work with me with the other problems, and you kind of get your experience base built up so that when you're on a test or an exam, you're not stressed out about it. You just apply what you've learned, use your intuition, and say, well, that worked last time, I'm going to do that. So I would suggest that you work this problem by yourself, make sure you get everything correct, because even though you've seen it once, doing it yourself and getting the signs straight and knowing what to do is a skill that you really do need to practice. So go do that now. Follow me on to the next section. We'll continue working more problems. Hello, and welcome to this section of the Circuit Analysis Tutor. In this section, we're going to continue working with the node voltage method of circuit analysis, but we're going to introduce a twist, and that is we're going to apply node voltage method to circuits that have dependent sources. A dependent current source or a dependent voltage source, doesn't matter, but we're going to learn how to use node voltage with those problems. Because if you look back at all of the node voltage problems that we've done up to this point, we haven't had any dependent current sources in there or dependent voltage sources. So it's an important skill, and it's something you'll definitely need to know for your homework and your exams. So here is an example problem. Here's the problem we're going to work today. We have a known voltage source here, a known voltage source over here as well, but notice this one's connected backwards, so it's kind of flipped over. Then we have some resistors everywhere, and then we have this dependent current source, again with it sort of flipped upside down, where the positive side's down and the negative side's up. And the voltage that is supplied by this source is dependent on another current. We call it I delta. I mean, in this case, it could be I1, it could be it doesn't matter what the label is, but it's dependent on some other current. It happens to be dependent on the current in this leg. So the way this works is whatever the current is here, like if it's 3 amps, you take 3 times 1.6, that number is going to be the voltage that's supplied. So once you turn the circuit on and everything settles out, the voltage supplied here is going to be 1.6 times the current over here. It turns out that when you just try to apply the node voltage method straight out, you'll quickly find that you need to think a little bit. But what I want to encourage you to do is when you see a problem like this, I want you to attack it just like you would any other node voltage problem. That way it doesn't seem like some different technique. There's nothing different about it. It's just that you have to know how to handle it in the context of node voltage. So you're going to find it's not that hard. So what we need to do first is look at this circuit and identify our essential nodes, which is always the first step. Well, this one's pretty simple. So we have an essential node up here and we have an essential node down here. You know, we have nodes interconnecting elements other places, but those only connect 2 items. Essential nodes are things that connect 3 or more items. So that's what we have here. We have 2 of them. And we've already learned that since we have 2 essential nodes, we expect to actually have only 1 node voltage equation. It's 1 minus the number of essential nodes we have. So next we have to choose a reference. It's pretty obvious in this case. We're going to choose this one because there's only 2 nodes to choose from, and we're always going to choose the bottom node when we can. So that's going to be our reference node, so I'll draw that in red. And what we're trying to actually do in this problem is find out what is the value of V naught. That's not the voltage across this source, that's the total node voltage up here. So when you look at what the problem's asking you, it's basically asking you, without saying it, what is the node voltage up here at this intersection? That's another way that this problem could be formulated. What is the node voltage up here? Of course, that's a little easy. It tells you, oh, you have to use a node voltage method, find out what the node voltage is here. Not quite stated in this way, but it's something that you have to know how to sort of interpret. So what we need to do is figure out what the node voltage is up here. Now, there's only one node, but just for completeness, I'm going to put number 1 up here. This is node 1 that we care about. Let's write the node voltage equation at this node, just like we would do for any other problem. So we're trying to figure out the current leaving this node going this direction, the current coming down here, and the current going this direction, and we're going to basically sum them up. This is exactly what we've been doing all along. So the node voltage at node 1. Node voltage at node 1. And I'll switch colors just to break it up a little bit here. So what we're going to have is, the node voltage here is V naught. So what we're going to have for this current over here is V naught minus what? Minus 186. That gives us the voltage drop across the 22 ohm resistor going that way, divided by 22. This is the current flowing this way out of the node. So V naught minus 186 over 22. Next, let's find the current flowing down this branch here. So it'll be plus. Again, the node voltage is V naught minus what? Well, we have a voltage source here, right? So we have a voltage source here. So we're trying to find the voltage across this resistor, right? So that we can divide it and find the current. So we have V naught minus the source divided by 14. The only trick is this source, if you really kind of compare it, it's flipped over backwards. Typically a node voltage, we pop up to our node voltage, we subtract the adjacent voltage in the other leg, and we divide by the resistance. Here we're doing the same thing. We pop up to the node voltage, we're subtracting the other voltage in this leg, but this voltage happens to be flipped upside down compared to normal, right? So it'll be negative 1.6 I delta. So we're subtracting a negative voltage, basically. We're dividing that by the resistance in this leg. So what we're trying to do here is find out what's the voltage across this resistor. The voltage is V naught minus this little voltage, but this one happens to be flipped backwards, so we're going to just do subtract a negative. In the end, we're going to end up adding. But I don't like just writing down this plus this, because then you're like, how did he do that? It's always just taking it and subtracting the other voltage, and then that's what we're doing. It's just in this case, it's negative, the thing that we're subtracting. So after this, we're going to have the third guy. So we'll have a plus, the current going this direction. So what we have is we pop up to our node voltage, V naught. We subtract any other voltages along the way, but of course this is also written in a negative term because it's flipped over backwards from normal, so it's minus a negative 43. There's no more voltage here. We'll divide by 2 because this is a resistor down here at the bottom. This is the node voltage equation at this node. Now there's really no other node voltage equation to write, right? This guy expressed the current in this leg, this guy expresses the current in this leg, this guy, we're subtracting a negative only because this is upside down. It really describes the current in the third leg. There's no other node voltage equations to write because I only have 2 nodes and one of them is my reference node, so that's the only place that we write an equation. So we look at this. First of all, now that I've explained the reason why we have subtracting the negative, now I'll go back and I'll put plus, because that's just algebra, right? So this is really V naught plus 1.6 I delta and V naught plus 43. I'm just trying to save a little bit of board space in writing the whole equation again. Now we look at this and say, all right, we only have one equation, let's solve it. So then immediately you get stuck because you have a V naught and you have an I delta. And so there's actually 2 variables in this one equation. See, typically with a regular node voltage problem that doesn't contain any dependent current sources, if you have a very simple one like this with 2 essential nodes, you expect to write one node voltage equation, and we've actually done that before. That node voltage equation just contains one variable. You solve it, and you solve the problem. This case, we tried to apply the node voltage method straight out of the gate exactly like we would, and we find that we have a problem. We have one equation, but 2 unknowns. So you need to kind of get in the habit of expecting that, I guess is what I'm trying to say. When you introduce these dependent current sources, you're going to introduce another variable into the equations. In this case, we introduced an I delta. It's inevitable. It's going to happen. Anytime you have a dependent source, it by definition means that you're referencing some other current or some other voltage in the circuit that is not part of the node voltage equations usually. So when you introduce it, you need to figure out a way to eliminate it basically. So what you need to get in the habit of doing is write the node voltage equations. In this case, there's only one, just like you would. Then you count your variables and you say, well, I've got 2 variables. So now I need to write another equation somehow so that I can have 2 equations and 2 unknowns. So you go back to your dependent source. The secret is going to lie here. We need to write what we're going to call a constraint equation. The constraint equation is going to arise because we have this dependent source there because we're referencing I delta. So the bottom line is when you write your node voltage equation, you figure out how many more equations you need based on the variables you have. In this case, we need 1 more equation to be able to have a system to solve. And then we go back and write that equation. Usually it's going to involve the dependent source. So we need to write some kind of equation for I delta. And then we notice that, yes, this is 1.6 I delta here, but I delta is labeled up here. This is the current. So what we need to do, let me switch colors here. So I'll write, in black, I'll write constraint equation. And I'll write it in green. So we look up here and we say, well, I delta is here. Let's write an equation involving I delta, right? Okay, so what would the current be up here? The current here, actually we just wrote it a minute ago. It's pretty easy to write. The current here, I delta, is equal to V naught, that's the node voltage, minus, we go around, minus this voltage, but this voltage is flipped upside down, so it's negative. So it's negative 43. And then there's no more voltage. Divide by 2. Doesn't this look familiar? It looks kind of similar to what we wrote here, but that's okay. So the bottom line is that I delta is equal to V naught plus 43 over 2. So what we do is we write the node voltage equation. This is what the node voltage equation is, all right? And then after that, we write the constraint equation. The constraint equation also involves I delta. And so this locks it down. We have 2 equations and 2 unknowns. This one involves V naught and V delta. This one involves V naught and V delta. So now we can actually solve the system. And the way you're going to solve the system is you're going to take the value that we just calculated, you're going to plug it back into here. And then you're going to get the answer. So what we're going to end up doing in the end is we're going to take this guy and we're going to substitute it in over here. All right, so what we want to do first before we substitute in for this is we want to simplify this equation as much as we really can, get rid of these fractions. So let's go ahead and multiply this equation by 22 all across the board. It's not going to lead to a perfect equation, but we'll at least get rid of this in the bottom, get rid of this in the bottom, and when we do the multiplication, we'll kind of introduce some decimals there, but it's sort of unavoidable at this point. So when we multiply by 22, we're going to cancel top and bottom. We'll be left with V naught minus 186. So V naught minus 186. That's going to be left there. When we multiply by 22 here, it'll be 22 divided by 14. 22 divided by 14 is a decimal, is 1.57. So we'll just have to kind of live with that, 1.57. And in parentheses, we'll just have V naught plus 1.6 I delta. V naught plus 1.6 I delta. Okay, now when we multiply this term by 22, 22 divided by 2 is 11. So we'll have 11 open parentheses, and what we'll have in the top is V naught plus 43. V naught plus 43. And all of that stuff is going to be equal to 0. So it's a little bit ugly, but in this case it's kind of unavoidable. So what we'll do at this point is let's multiply this in and collect terms into something nice. So what we'll have is V naught minus 186, and then we'll have plus 1.57 V naught plus, what's 1.57 times 1.6, 2.51 I delta, okay? And then over here, we'll distribute this in, 11 V naught plus 11 times 43 is 473. And that's going to be equal to 0. So now what we need to do is combine terms. We have 1 V naught here. 1.57 V naught here, and 11 V naught here. And when you add all of these things together, what you're going to get is 13.57 V naught. Okay, so we've taken care of this term here, and this term here. So the only other thing we really have is this I delta, 2.51 I delta. All right, and then we have the constants. Negative 186 plus 473 is going to be equal to 287 is equal to 0. Okay, so we've simplified that equation. We have V naught and I delta. Now what we need to do is substitute in for the I delta that we actually know. So let's write that down over here. So we'll recall that I delta is V naught plus 43 over 2. That's what we had before from the last time. So let's substitute that in. So what we're going to have here, 13.57 V naught plus 2.51 times I delta. So let's open the parentheses, V naught plus 43 over 2 plus 287 is equal to 0. Okay, so we're basically to the end game now because we just need to solve for V naught, and that's what we're trying to find anyway. So we'll have 13.57 V naught plus, here we have 2.51 divided by 2 for the first term here, and when you get that, you'll get 1.26 V naught. Basically, we multiply this into V naught, and then we divide by 2, and we get that. For the next term, we need to multiply into 43 and then also divide by 2. When we do that, we'll get 53.97. Multiply in, divide by 2, 53.97. Then we have plus 287 is equal to 0. Okay? And so finally what we're going to have, when you add these two terms together, 13.57 plus this, you'll get 14.83 V naught. Plus, you add these terms together, you'll get 340.9. All right, so then what we have, when you move this over, you'll have 14.83 V naught is equal to negative 340.9. All right, and for the grand finale, V naught, when you take this and you divide by this, negative 340.9 divided by 14.83, you're going to get something extremely close to negative because of the negative sign, 23 volts. I think it's like 22.999 or something like that. So you get basically negative 23 volts. And that's the answer. So the question started out by saying, here's a circuit, figure out with node voltage method, what is V naught? Okay, what is the voltage at this node? Basically, what's the node voltage up here? So we start by writing a node voltage equation, but when you do it, you realize you don't have enough equations because you have an I delta running around. So you have to write some kind of constraint equation involving the new variable that you've introduced, which is I delta. And so we look around and we write an equation for I delta. That's just V naught minus this voltage, which was negative, divided by 2, and that's going to be V over R, so that's going to be what I delta is, what that current in that leg's equal to. So the rest of it's algebra. We go and we simplify this guy down. Once we simplify it down, we get this. Then we plug in what we know for I delta here, and again, we continue simplifying, one equation, one unknown, we find V naught. Now, it's always good to look and see if this thing makes physical sense, right? And I think it does. What we figured out is this V naught is negative 23 volts. That means that the way I have it drawn is backwards. Really, the voltage is flipped upside down where it's negative and then positive down here. Does that make sense? I mean, you could never tell ahead of time if it does, but I think you could convince yourself that it does. I mean, here we have a very large voltage, positive, negative. So at first glance, you might say, well, this voltage is probably going to be positive, negative because this is so large. However, we have 43 volts flipped over. You can think of these as batteries. This is an energizer up this way, plus minus. This is an energizer battery, minus, plus minus, flipped totally upside down. So, okay, this is a little bit smaller, this is a little bit bigger, so I would still expect this voltage to be in this direction that it's drawn. However, look at this voltage source. It's flipped upside down also, and it's 1.6 times whatever this current is. So what basically ended up happening is this current was large enough to make this voltage large enough, to drag the whole thing and basically flip it upside down. So even though I have 186 volts in this orientation, the fact that I have this guy flipped upside down and this guy flipped upside down, and the way the currents all worked out made everything large enough so that V0 actually is not oriented in the direction that I've drawn it. It's actually also flipped upside down. So you've got big voltage on one side of the circuit, some other voltages on the other side, but that are backwards. It forces V0 to flip the other direction. So it makes physical sense. It's not something that you could see ahead of time and convince yourself with certainty. But in retrospect, looking at it, you can kind of get a sanity check, which is always good to do. So we're done with this problem. We're going to do a couple of more that'll kind of ratchet up the complexity. This one was sort of easy because it was just one node that we cared about up at the top. And the constraint equation was also pretty simple, but I wanted to do it so that you could get practice. The way you do these problems with node voltage is you write the node voltage equation, you see how many variables you have that you've introduced with your dependent sources, and then you write these constraint equations. You're going to end up substituting them in and solving the system as usual. So it's kind of an extension or an expansion of the basic node voltage method that we've always learned, okay? I'm Jason with MathTutorDVD.com. Follow me to the next section. We'll do another one of these guys that's slightly more challenging.